In algebra, we learned that the equation of a line could be written as y equals mx plus b, or as y minus y1 equals m times x minus x1, where x1, y1 was a point on the line. And in the case of this slope-intercept form, the point that we're talking about here is the point B, which is the y-intercept. That is still a point. It has coordinates 0, comma something. I'll call it y1 to correspond to this y1 here. And what that really means in either case is that if we have a point somewhere and a slope, which you can think of as a direction, right? A slope, a steep slope maybe looks like this, whereas a shallow slope maybe looks like that. A really shallow slope maybe looks like that. A negative slope looks like that, right? And each one of these is a kind of a direction. Well, in R3, we can do the same thing. If we have a point, floating in space somewhere, and a direction of some kind. The direction, well, let's go back to the point for just a second. Let's call this point x naught, y naught, z naught. This could be x1, y1, z1, or it could be x1, x2, x3. I just happen to be using this notation because in the presentation of the equation of a line in space, which is what we're getting to here eventually, I find it helpful to have the x, y, and z notation in place for reasons which I think will become obvious when we get to that stage. But I need to distinguish x, y, and z, just any old x, y, and z, from some specific yet still generic x, y, and z. These are the 0th x, if you will, the 0th y, or the starting point x, the starting point y, the starting point z, something like that. So these x naught, the subscripts here just distinguish this point, this specific yet still generic point, from the general, the variables x, y, and z. So I'm going to call my point x, y, z. And instead of a slope, we're going to use something called a direction vector, because we now know how to deal with vectors. And that will be, again, once we get going here, it'll be easy to see how to use that. So we're going to call our vector v. And we'll just use the components of vector v, a, b, and c. At this point, I think it might be better to have a better drawing to go with. So I've got one ready here for you. And I'm going to get rid of some of this earlier stuff we were talking about. And let's see, I'll make this a little bit bigger. All right, that's much better. Now, let's take a look at this line that we have in space here. This is the XY plane down here, the XZ plane over here on this wall. The back wall here is the YZ plane. And this line is just floating in space. The point P here is at some number of coordinates x, y, and z away from the origin, as is the point Q. But here's my point P, x naught, y naught, z naught. And here is my vector ABC. It's just a generic vector ABC, but it has the property that it's parallel to this line. And that's why we call it the direction vector. Remember that I can pick this vector up from where it is just now and move it anywhere I want. I can put it up here, I can put it out here, I can put it on the line, and that's what's important here. We're using the directional component, or the directional features of the vector, even though it's in a different position than our line. We're going to use its function as a directional guide. In a way, then, we can say that the line PQ can be thought of as some scalar of the vector v? Well, the line PQ can be thought of as a vector in its own right. We have x minus x naught, y minus y naught, and z minus z naught as the components of that vector. You'll notice that while P has the specific but still generic components, actually coordinates, these aren't components, x naught, y naught, and z naught, Q could be any point on this line, and it has coordinates x, y, and z. It's just some other point on the line. So we're getting these components for the vector PQ by looking at the differences between the x coordinates, that's x minus x naught, the y coordinates, and the z coordinates. Okay, so that's what we're changing the language of the label PQ to the specific vector PQ. And that is equal to a scalar times the vector v. But we said earlier that the vector v was going to be a, b, c. Now, if I use vector addition, or subtraction to be more accurate, on the left-hand side, I can unsubtract together. I'll get the first, second, and third components of the first vector minus the first, second, and third components of the second vector. Right, so if I gave you this vector subtraction problem, you would say, well, that's just x minus x naught, comma, y minus y naught, comma, z minus z naught. And I've just done that in reverse. And that's still equal to t times a, b, c. I need more room as usual, and I don't think I need this diagram anymore. I'm not going to get rid of it completely, but I think I will shrink it, and I'm not sure what's going to happen with my green vector when I do that, but I guess we'll find out. Okay, well, that's not terribly surprising. The green vector did not go with the diagram, but I've just moved it anyway. I'm not sure if I'm going to need it again, but just in case I do, I'm going to leave it there. Okay, now I'm going to take the this vector here, x naught, y naught, z naught, and I'm going to add that vector to both sides. And just as in algebra, if I add the vector x naught, y naught, z naught to both sides, then these two copies add up to 0 and they cancel each other out. So now I have the equation x, y, z equals, and I'm going to put this vector first, x naught, y naught, z naught plus t times the vector a, b, c. Now, in keeping with, in order to be consistent across multiple disciplines in mathematics, I'm going to rename the vector x, y, z. It is a vector, and I'm just going to call it vector r. I'm also going to rename the vector x naught, y naught, z naught. It's a specific vector, a vector with specific values. We just don't know what they are. They're the coordinates of some point, right? Some point P, x naught, y naught, z naught. We just don't know what those coordinates are. And they could be the coordinates of any point, but they're not generic in that sense. They're the specific coordinates of a point in a problem without our knowing what those values are, as opposed to being like x, y, and z, kind of a movable point. This point could be anywhere on this line. This point is this specific point on this line. We just don't know what those values are. So I'm going to call the vector x naught, y naught, z naught vector r naught. And then I have plus t times, and you'll probably recall that this was originally vector v. I didn't really need to rename it here, but because I was working with components throughout the rest of this problem, I changed this this v into ABC just so that for consistency. What we have here is called the vector equation of a line. What's interesting about this is if we go back a step and look at maybe even two steps. If we go back up to, oh gosh, maybe all the way up here, you can see that component by component, in order for this equation to be true at any step along the way, the components have to match. So if I multiply t through ABC, the vector ABC, then I'm going to get TA, comma, TB, comma, TC. And so for this equation to be true, it must also be true that x minus x naught equals TA. You can also see that down here. X has to equal x naught plus TA. In this version, the x naught was on the left-hand side of the equation. In this version, it's on the right. So it sounds a little different, but it's really the same thing. So I have this series, I guess, of statements. X has to equal x naught plus t times a. But then the y components have to match as well, and the z components. So I also have the sentence y equals y naught plus tb, and z equals z naught plus tc. This collection of equations, let's get them all in there, are collectively called the parametric equations of a line. Now, if I take this equation here, let's put this off to the side. X equals x naught plus TA, and I subtract x naught from both sides. I get x minus x naught equals TA. That's very similar to what I had up here. X minus x naught must equal TA. And then I divide both sides by by A. I get x minus x naught over A equals T. If I do the same thing for all three of these equations, the x, the y, and the z, then I end up with x minus x naught equals T, y all over A, y minus y naught all over B equals T, and z minus z naught all over C equals T. Well, if these things are all equal to T, then they must be equal to each other. And so I get this, x minus x naught over A equals y minus y naught over B equals z minus z naught over C. And this collection of equations is collectively called the symmetric equations of a line. Your textbook doesn't present this version, but you do see it in other textbooks, and I have found that a lot of students taking linear algebra are either taking Calculus 3 at the same time. Well, Calculus 3, that depends on where you take it. Vector calculus, introductory vector calculus. Some institutions teach that as part of the early curriculum for Calculus 3. Others teach Calculus 3 strictly as multivariable calculus, and all of vector calculus goes into Calculus 4. So it kind of depends on where you're taking it. But your textbook doesn't present this, but a lot of textbooks do. And if you're taking vector calculus at the same time, or you've already taken it, or you're planning to take it in the future, it's very likely that you'll see this version of the equation of a line in R3. So I wanted to throw that in there for you. But your book uses this version, the vector equation, and it uses a form of this version. It actually uses, let's see, it's kind of like, I can't find it now actually. Oh, it's this one here. So it's the vector equation of a line, but it hasn't been written as vector labels. It's been written out as vectors. So I guess we could highlight that as well and say this is another version of the vector equation of a line. And your textbook gives you these. So let me do this. Let's highlight these labels, these titles here in yellow. These are the two that your textbook uses and that the exercises in your textbook will likely be asking you to be familiar with. Now, one of the things that I'd like to point out here is that you really only need to memorize one of these. Of course, I don't believe in memorizing per se anyway. In the field, as I like to say, instead of in the real world, in the field, if you've forgotten the vector equation of a line, chances are you're just going to look it up, or you're going to ask one of your colleagues, what's that equation again? So most likely you could put this on a note card to have handy while you're studying or while you're taking an exam or whatever. But really you only need to have one, and here's why. This r equals r naught plus tv is just the label form of the equation above it. R is just what we call the vector x, y, z. R naught is what we call the vector x naught, y naught, z naught. T is just a scalar, and v is a, b, c. And v, remember, is our direction vector. That's this one over here. It's not on the line. It's just telling us which direction the line is going in. And then I've got these lined up, got these written in this order, as if you will, for a very specific reason, and that is this. If you look above r, you see the vector that r is. If you look above r naught, you see what that vector is. And if you look above v, you see that vector. If you look below r, you see each of the components of r. R naught has each of the components of r naught below it, and v has each of its components below it. And so really r is just x, y, z, x, y, z. R naught is just x naught, y naught, z naught, x naught, y naught, z naught. This is a series of 3 equations, but each one is the equation of the components of these other equations, right? So really, this is the only one you need, or perhaps this is the only one you need, and then this other one follows from that. Okay, that's the formulas. Let's take a look at an example. Write the equation of the line in R3 that passes through the point 6, 0, 7 and is parallel to the vector 2i plus 4j plus 3k. Well, there are a couple of things to note right off the bat. This 6, 0, 7 is my x naught, y naught, z naught. It's a specific point, and now that I'm not talking about the theoretical aspect of this phenomenon, I can talk about not the unknown but specific value x naught. I can say that's 6. The other thing that I noticed right off right from the very beginning is that this vector right here is the one that my line is supposed to be parallel to. So the first thing I'm going to do is write this in component form, 2, 4, 3, and then I'll note that that is my vector v. So I have a couple of different ways that I could write this line. I'm going to start by reminding myself what the sort of formula is. This is the one that I have memorized. I don't actually. I do by the time I get to this point in the quarter, but if it's been a while since I've taught the class, then I have to remind myself what the formula is. This is I've written this x naught, y naught, z naught. This is my r naught. And here I have my v. So literally all I have to do is write out what those vectors are. 6, 0, 7 plus t times 2, 4, 3. And that's it. The thing is, it's not quite it, because there are other ways we could write this line. We could say, for example, x equals 6 plus 2t, y equals 0 plus 4t, and z equals 7 plus 3t. This is also a way to write this line in 3-space. Interestingly enough, vector v is our direction vector, but it's just a direction. It doesn't matter how long it is. So I could use a scalar multiple of v, let's go 3v, which is equal to 6, 12, 9. I could use that as my direction vector. So then I could also write x equals 6 plus 6t, y equals 0 plus 12t, z equals, where am I, 7 plus 9t. And I could write that instead. That equates to r equals 6, 0, 7 plus t times 6, 12, 9. So depending on whether I want it in vector form or in parametric form, I have a couple of different ways of writing it, and I have an infinite number of ways of sort of representing it if I wanted to. I could, should I so desire, use 1/5 v as my direction vector, which would give me 2/5. I mean, I wouldn't, right? This is silly, but it'll give you the idea, I hope, that you can use any direction, any vector, as long as it's pointing, any vector for v, as long as it's pointing in the same direction as v. That's effectively our slope, right? It's taking the place of the slope in R2. So a third vector equation for this line would be r equals 6, 0, 7 plus t times 2/5, 4/5, 3/5, or x, y, z equals 6, 0, 7 plus t times 2/5, 4/5, 3/5. Well, that's extreme. You know, nobody's actually likely to do that in reality. There's no point in making a problem messier than it actually has to be. My point is that there are multiple ways to do this. We haven't even dealt with the symmetric version, and we're not going to. I have a question lined up for you on the interactive homework that is very much like this. It asks you, it gives you a point, and it gives you a direction vector, and it asks you to determine which of us. It's a multiple choice question. It's a multiple answer question. It asks you which of the equations below represent the line through the point and using the direction vector. And it gives you several options. It gives you, let's see, 3, 4, 5, 6, like 8 options, and several of them are correct because there's more than one way to do this. Okay, so that's how you write the equation of a line in 3 dimensions. There is more than one way to write the equation of a line in 3 dimensions. And because the direction vector is literally just contributing its directional feature, the length of the vector doesn't matter. And so we have an infinite number of vectors we can use. Notice that I'm not allowed to change vector r0. I'm not allowed to change these at all because the line has to go through that point. If I change this at all, if I double this vector, I get 12, 0, 14. That's a different point, right? So in order to guarantee that it's going to go through this point, I can't change this vector, but I can change this one by scaling it.